Welcome dear students. Today we are going to see video lecture on course code U18Esit404, course name Digital System Design. And I'm Dr.B.Dhanalakshmi, Professor, Department of Information Technology, working in Bharat Institute of Higher Education and Research. And today we will see the topic in Unit 3, Latches and Flip-flops. So first we will see the introduction about sequential circuit. So sequential circuit consists of feedback path and memory elements. So compared to the combinational circuit, we have memory element here additional to the other gates in combinational circuit. So here in sequential circuit, it comprises of combinational logic gates and memory elements. So here the inputs we are sending and the outputs we are getting here along with analyzing the data stored in the memory element. So we also have clock pulses here which can be embedded in each and every phase. So there are two types of sequential circuit. The first is synchronous circuit where the output change at certain time, and asynchronous circuit where the output change anytime. And sequential circuit belongs to the multi-vibrator category where it can have the different forms like bistable form, monostable form, and astable form. So bistable form means consists of two stable conditions, and monostable form consists of one stable condition, and astable form which consists that is no stable condition. So bistable logic device is latches and flip-flop. So latch and flip-flop differ by the method which is used to change the stable condition. And now we will see about memory element, where the memory element device that can remember a value for a certain period of time or change the value based on the input instruction given to the circuit. And in latches and flip-flop, we have the memory element where the commands for the latches include set and reset command. And flip-flop is a memory element which change its condition based on the clock signal given. So the clock pulse is always a square waveform where we have positive edges and negative edges. So positive edges where the transition is from 0 to 1, and the negative clock pulse, that is negative edges, where we can find the transition from 1 to 0. So here we can see the positive pulses and the negative pulses here alternatively in the clock square waveform. And as we discussed, there are two types of trigger or activator. First is pulse triggered and edge triggered. So pulse triggered we can find in latches where on condition, on state condition is represented by value 1, and off condition or the off state is represented by value 0. And next is edge triggered, which we can find in flip-flops where the positive edge triggered, here the on means positive pulse means when 0 to 1 transition occurs, and the positive edge triggered will be in off state at other time. And when negative edge triggered is considered, the on state means when the transition occur from 1 to 0 and off state at other time. And now we will see about SR latches. Output always has complement Q and Q dash. And when Q is high, the latch is said to be in set condition. And when Q is low, the latch is said to be reset condition. And for SR with active high input, also known as NOR gate latch, and here R is high and S will be low at reset condition, and in set condition the S will be high and R will be low. If both R and S values are low, then it shows no condition change. And if both are high, that is, if both R and S are having value 1, in that case, Q and Q dash becomes invalid. So for all S dash R dash here, we are going to implement with NAND gate latch. And previous example we saw implemented with NOR gate latch, and here S dash R dash input we are going to implement using NAND gate latch. Here S dash R dash with active low input, where R is equal to low and S is equal to high in reset condition. And when set condition in SR latch, the S is equal to low and R is equal to high. And when both S and R values are high, then no condition change. And both low, then Q and Q dash becomes high. That is invalid. And here is the diagrammatic circuit representation SR with active high input. So the first example, we can see the NOR gate implemented with S and R input values. When S and R values, where S is 1 and R value is 0, then we get the Q value as 1. And Q dash is a complement of Q, that is 0. And then when S value is 0 and R value is 0, then we set the Q value as 1 and Q dash value as 0. And here the NOR gate implementation. So according to that, the state table has been, and the Q and Q dash values are determined. The output values are determined. And we can see the first NOR gate having the R input and SR S input and R input. And here the output of the first NOR gate having S input, that is Q dash, is again sent as the input to the other NOR gate, and Q, the output Q is sent as the other input for the alternate, that is next NOR gate. And when S value is 0 and R value is 1, we get Q value as 0 and Q dash as 1. And when S and R values are 0, then Q value is 0 and Q dash is 1. And when both are said to be 1, that is S value is 1 and R value is 1, which determines the invalid state. And the second circuit shows the implementation using NAND gate. That is, you can see two NAND gates, okay, where the first NAND gate has S dash as the input and Q dash as the input, and the other NAND gate has Q as the input and R dash as the input. So here the state table shows the different output values at each and every situation, where S dash 1 and R dash 0, we get Q value as 0. And when S dash and R dash are 1, then Q is 0 and Q dash is 1. And when S dash is 0 and R dash is 1, we get Q value as 1 and Q dash as 0. And when both S dash and R dash are 0, which determines the invalid state. And here SR with high input, that is active high input, where we can say 0, 0 given as input for S and R, then no change in Q value and Q dash value. So the latch will remain in the present state. There will be no transition in the output values. So the output values retain the present state. And when S is 1 and R is set to be 0, then Q value, the latch is in set condition now. So Q value will be 1 and Q dash is 0. And next is reset condition in latch, that is S is 0 and R is 1, where Q value is 0 and Q dash is 1. And when S and R values are 1, then this shows the invalid condition. And next we have S dash R dash with active low input. So S dash R dash, when both are having 1, then there is no change. The present state remains in the latch. And S dash R dash are 0 and 1 respectively, then the Q value is 1 and Q dash is 0, which is said to be the latch set condition. And in latch reset condition, we have S dash and R dash as 1 and 0, where the output values will be Q as 0 and Q dash as 1. And last is when both S dash and R dash are 0, 0, then Q value is 1, Q dash is 1, which is said to be invalid condition. And here we have enable input. Apart from S and R, we have enable input and two NAND gates, that is SR latch with two NAND gates and also two OR gates all together in the combinational circuit along with the memory element. So it forms a sequential circuit. So apart from S and R, we have enable input here and two outputs Q and Q dash. So the SR latch with gate. The output change here, if needed, only when enable condition is set or reset based on it. Which condition is said to be invalid? Let us see the state table now. The enable condition, if it is 1, okay, so enable condition 1, in that case, S and R value, and based on the present output, that is Q value, the next state Q value can be determined. So when S and R values are 0 and the Q, the output present state value is 0, when the enable input is 1, then you have the next state as 0. And when S value is 0, R value is 1, and the present state is also 0, in that case the Q, the next state value, Q of t plus 1 is 0. And when S is said to be 1, that is set condition, in that case your next state value will be 1. And when both S and R values are 1, then it is indeterminate state, that is invalid. And when the present state, that is present output Q value is 1, in that case, when S and R values are 0, then the next state value is 1. When S value is 0 and R value is 1, then the next state value is 0. And when 1 is set to be S value and 0 R value, then the next state value will be 1. And again the invalid condition where S and R values are set to 1, then it forms a invalid condition. So we can say, consolidate and say that when S and R are 0 and the Q value remains the same even in the next state, that is no change. And when S value is 0 and R value is 1, then the next output, next state value will be 0, which is reset condition. And when S is 1 and R is 0, then the next state value will be 1, which is set condition. When both S and R values are 1, then it shows the indeterminate state. And here you can derive the state equation for the next state, that is Q of t plus 1 as S plus R dash into Q, current state. That is S dot R is equal to 0. So this is the state equation for the current shown state table. And now we will see the D latch with gate. Make the input R the same as S dash and D latch with gate. And here the D latch eliminate the invalid condition in SR latch. So here the D latch And instead of SR latch, we had two inputs S and R, but here in D latch, we are having single input D, and D dash is sent to the other NAND gate. So now we'll see the D latch with combinational gate circuit. When enable is high, then D is high when the latch is in set condition, and D is low when the latch is in reset condition. That is, when enable is high, Q will follow input D. The criteria state table is given here. That is, D value when it is 0 in enable state, enable is 1. Then the next state will be 0 under reset condition. And the next is set condition where enable is 1 and D is also 1. And the next state value will be 1. And when enable is 0 irrespective of the D value, then the Q value, the current state will retain for the next state also. That is no change. So when enable is 1, we can say the next state Q of T plus 1 is as same as the D value. Now we will see about the edge triggered flip-flop. So flip-flop here, bistable synchronous device where the output change its condition at certain point on input trigger named clock. So condition change either at positive edge, up edge, or at negative edge, that is down edge of clock signal. So here we can have positive edge and a negative edge alternatively in the diagram, which where the clock signal in the square form is shown. So here in the edge triggered flip-flop, the flip-flops SR, D and JK edge triggered flip-flop is marked with the greater than symbol at the clock input. And the negative edge triggered flip-flop where we can see a circle symbol near the clock pulse with the greater than symbol, which shows the negative edge triggered clock pulse. And now we will see the SR flip-flop working when the clock pulse is included. So SR flip-flop at edge triggered clock pulse. So the set condition will be when S is high and R is low, and the reset condition will be when R is high and S is low. Both input low, then no change, and both input are high, then it is said to be invalid condition. So here the state table for edge triggered SR flip-flop is given, where S is 0, R is 0, and the clock pulse is irrespective of the clock pulse, then the present state QT will retain for the next state also QT plus 1. That is no change. And when S is 0 and R is 1, that is the clock pulse transition from 0 to 1, low to high, then the next state output will be 0. And when S is 1 and R is 0, and when you see the clock transition from low to high, then the next state value will be 1, which is set condition. And when S and R are both 1 and the clock pulse transition from low to high, then we can say the next state value we cannot find, it is invalid. Now we will see the three parts in SR flip-flop. There is NAND latch, pulse steering circuit, pulse transaction circuit detector or edge detector. The pulse transaction detector circuit will detect up trigger and down trigger and produce very short spike duration. And here is a pulse transaction detector where it can detect the clock pulses which is sent as the input for the XOR flip-flop. So here the positive going transition rising edges are shown. So in the first time transition, we can see the transition occur from low to high, and then in clock dash, we can see the transition from high to low, and the different clock pulses at different stages are given here in the diagram as a rising edges. And negative going transition are shown here as the falling edges, where we can see the transition from high to low clearly. And now we will see about the D flip-flop, where one input D along with the clock pulse here. So D is said to be high under set condition and D is said to be low under reset condition. So Q will follow D at clock edge, and to change the SR flip-flop to D flip-flop, we have to add the inverter. So here the positive edge triggered D flip-flop formed along with the SR flip-flop. So here S is the input D and R is the inverter of D. So when D is 1, under positive clock pulse, the next state value will be 1, which is set condition. And when D is 0 and having clock pulse as a positive clock pulse, that is transition from low to high, and the next state value will be 0, which is reset condition. And here we'll see the JK flip-flop where there is no invalid condition. Instead, there is a toggle condition here. J is equal to high and K is equal to low, which is set condition. And K is high and J is low under reset condition. And when both inputs are low, then there is no change in the state value. But input high, then it gets toggled. So here is the circuit diagram for JK flip-flop, where we can see two NAND gates and two NOR gates, and the state table shows you two inputs J and K along with the clock pulse. So we can see that when two values J and K values are given as 0 and positive clock pulse is there, that is from transition of clock pulse from low to high. In that case, the present state will retain for the next state also, where there is no change in the output value. And when J value is 0 and K value is 1 and the high positive clock pulse, then your next state value will be 0, which is reset condition. And when J value is 1 and K value is 0 and a clock pulse, positive clock pulse, then the next state value will be 1, which is set condition. And when both inputs J and K value are 1 in positive clock pulse, then the present state gets toggled, that is inverted for getting the next state. So here is a state equation given for finding the next state, where Q of t plus 1 is equal to J dot Q dash plus K dash Q. So here are the inputs given Q, J and K. Q is the present state output value and J and K values, and the corresponding next state value is given in the last column, that is Q of t plus 1 in the second table. When all the three inputs are 0, then the next state value is 0. And when Q, present state, and the J values are 0 and K is 1, then the next state value is 0. And the next state value will be 1 when J value is 1 or JK value is 1 or Q value is 1. And even when Q and J values are 1, we get the next state value as 1. In all other cases, we get the next state value as 0. And here we will see about the T flip-flop, where the single input version for JK flip-flop concept, which is formed by combining JK input. So here we can see the T flip-flop, T input given to the two NAND gates along with the clock pulses. So here the JK flip-flop the J and K values are same as the T value here, and state table is given where the T value when 0 in positive clock pulse, there is no change in the present value and the next state value. And when T is 1 under positive clock pulse, then it toggles the present state to the next transition state. And when the present state is 0 and T is 0, then the next state value is also 0. When present state value Q is 0 and T value is 1, then the next state value is 1. When the present state is 1 and T is 0, then the next state value is 1. And when present state and the T values are 1, the next state value will be 0. So the state equation which can be derived is Q of T plus 1 is equal to T dot Q dash plus T dash dot Q. And now we will see about T flip-flop where the usage is as frequency divider. So here J and K inputs are there where the T input is given to J and also K. And here it divide the clock frequency by 2, which is shown in the diagram here. So here the Q input is given for every 2 time units where the clock frequency is 2 here. And the next diagram we have the clock frequency by 4. So 4 transitions which can be shown in the clock pulse, so that represents one state in the output. And here we will see about the master slave flip-flop. So master is always activated. When it is activated, when positive edge and slave is activated when negative edge is triggered. So when positive edge transition from 0 to 1 occurs, the master is activated, and when negative edge is triggered, that is transition from high to low, then slave is activated. So here is the master slave flip-flop circuit which is given here. Here the JK flip-flop is given here where the master slave concept can be implemented. So we can see the clock pulse when there is a transition from low to high. In that case, master is activated. So we can see the transition first beginning from high to low preset condition, and then from low to high where it is toggled, the output is toggled, and which continues completely till the end of the clock pulse. So here we can see the NAND gates and the NOR gates implemented here in the master slave flip-flop, where we have the which is shown as the transition of the master flip-flop, and clear signal which is shown as the negative flip-flop for the negative edge triggered flip-flop. So preset condition, toggle condition, and we'll have the clear condition. So this is shown when J and K values are high. So here we can just implement this master slave concept in any flip-flop category, and here in this example we are using JK flip-flop along with the clock pulse. So as we discussed, there are how many flip-flops here? We started with SR latch, and then we saw about D flip-flop, and then we saw about JK flip-flop, then T flip-flop, and then we saw about master slave flip-flop. Okay, so these flip-flops mainly have memory elements, okay, which are implemented in the sequential circuits. Thank you for listening. We'll meet in the next video lecture.